So why does curl V equals 0 imply that Bernoulli's equation can be applied across streamlines as well as along streamlines? To consider this, we'll think about the forces and the acceleration around a fluid blob, so the mass per unit volume is rho times the acceleration dv by dt of a fluid blob is equal to minus grad p, so those are the pressure forces on the fluid blob causing an acceleration, and that's Euler's equation. So I shall expand out the material derivative, so we get rho partial dv by dt plus v dot grad of v is equal to minus grad p. And if I consider only steady flows, then this is 0 because the flow is steady, i.e. not changing in time at any point in space. So what I have now is rho v dot grad v is equal to minus grad p. At this point, I need to include a vector identity. You can find these online very easily. The one I'm going to use is that v dot grad v is equal to the curl of v crossed with v plus a half times the gradient of v dotted with itself. Now you don't have to remember these, they're all available online or in maths books, but after you've used them a few times you start to remember them. I'd just like to point something out really as an aside, which is that v dotted with v is a scalar, and it's just v squared, mod v squared, so it's just the speed squared, and we'd often write that as v squared. So let's substitute that into this expression. We're going to get rho times the curl of v crossed with v plus a half rho times the gradient of v dotted with v, and that's equal to minus grad p. Now these two terms, grad p and grad of v dot v, are just the gradients of two functions, so I can put them together and I'm going to get plus grad of a half rho v dot v. There's no problem putting the rho inside the grad because we have a uniform density fluid, so rho does not vary in space, plus p. That's equal to 0 on the right hand side, and on the left hand side I have, as before, rho times the curl of v crossed with v. And this is actually all I need, because look at this. If curl of v is equal to 0, then this quantity here, grad of a half rho v dot v plus p, is equal to 0. In other words, the quantity a half rho v squared plus p is uniform in space in every direction. And if you look at this, this is just the stagnation pressure P0, and if I'd included gravity, it would be the total pressure Pt. So what we have is that the stagnation pressure P0 is the same along every single streamline. And that is why, when curl of v is equal to 0, you can apply Bernoulli across streamlines as well as along streamlines, because it's the same on every single streamline. And actually, you can go even further than this. Let's scroll down a bit to make some space. And let's imagine now that curl of v is not equal to 0. In this case, the term on the left-hand side in the above equation is non-zero, but we know that we can apply Bernoulli along streamlines, so that's a streamline. We can apply Bernoulli along streamline. So what I'm going to do now is take the dot product of this equation here, take the dot product with the velocity along a streamline. I could do it with the unit vector along the streamline too, but it's just as easy to do it with the velocity because that is always pointing in the streamline direction. So if I do that, I'm going to get v dotted with, I'll put it all in square brackets, rho curl of v crossed with V plus V dotted with the gradient grad of a half rho V dot V plus P, and that's equal to 0. And now let's look at the term on the left-hand side in more detail. Rho density is a scalar, it can come outside. We've got rho times V dotted with omega, which is the curl of V, crossed with V. Now you probably already know that this is equal to 0, but let me just put in another line of working, because this is the same using another vector identity as rho times omega dotted with V crossed V, and that's clearly equal to 0 because any vector dotted crossed with itself is equal to 0. So what we have in this case is that for the case where we do take the dot product with V, this term on the left hand side here is equal to 0, and what we get is just this term on the right hand side equal to 0. Now let's look at this in more detail. We're saying here that the gradient of this function half rho V dot V plus P in the direction of the velocity vector is equal to 0. And this is just Bernoulli's equation along a streamline, because this is the stagnation pressure, and if I'd repeated it including gravity, that would be the total pressure, or the Bernoulli constant. So that's why you can always apply Bernoulli along streamlines even when curl of V is not equal to 0. Of course, this only works in inviscid flow. In viscous flow, you can't apply Bernoulli because you lose mechanical energy through the action of viscosity.